All right. So today we get our definition of two events being independent. Remember that two events are independent if knowing the um, probability of, or knowing whether or not, let's say that the right way, where one event occurring doesn't have any effect on the other one occurring, right? Sequential coin flips are independent of one another. If I draw a card from a deck of cards and it turns out to be, whatever, if I put the card back and then randomly select another card, what that card would has no effect on what the next card is. Now, if I don't put it back, then those are no longer independent because I've changed my sample space. So here's the um, definition of independent. Events A and B are independent whenever the probability of B occurring, given that A has already occurred, is equal to the probability of B. In other words, A's occurrence doesn't change, doesn't affect the probability that it's B. So, and this is the example, which is very much like the one that was on the homework, but let's do this. Use the table below to determine whether or not being a second class ticket holder is independent of survival or not. All right, so what we want to know is the probability of survival given that it, and I guess let's use A for alive on that. Given that they survived. So that's going to be the probability that they are alive and survived divided by the probability that they are alive. So the probability that they are alive and survived, and are a second class ticket holder, is the 118 out of the total 2,201. Whereas the probability that someone is alive is 711 divided by 2,201. I'm just going to leave it as 118 over 711 for now. What's the probability that they are alive? Well, we already figured that, didn't we? It's 711 over 2201. It's not immediately obvious that those two are not equal. So the first one, 118 divided by 711, is about 16.6%. And this is going to be way more than that. This is around a third. 711 divided by 2201. Yeah, it's 32.3%. It is not independent. by the way, on this, you could have done the opposite. You could have done the probability that they were a second class ticket holder given that they are alive, and compare that to the probability that they are alive. I mean, probability that they're a second class ticket holder. So you can do that either way. It doesn't make any difference. Okay. Hang on a second. Why do I feel like I have done something weird? Pardon me for just a second. I have. I was like, why is that the same? This should not be. This should be probability that they survived, right? It's divided by given that they survived. It's like, I shouldn't have that same number there twice. I apologize. The probability that they survived, I did the right thing.
I think it's you used S for second.
Oh, and I've confused myself like 3 times now on that.
Yeah.
So this should have been probability that they're alive. No, it should be probability that they're a second class ticket holder. Okay, I was like, that still can't be right. This is supposed to be S.
Another layer.
And the probability that they're a second class ticket holder is 285 over 2201. So let's see, 118 over 285. 41. Yeah, 41.4%. The way I usually think about it in the end on this is that second class passengers survived at a much higher rate than passengers in general. That's how I know those are not independent of one another. Okay, and I think just intuitively that kind of makes sense. So one of the things that students will sometimes mess up, even worse than what I just messed up, is this idea of independent and disjoint. Independent is never the same thing as disjoint. In fact, it can't be. Disjoint events can't be independent. Disjoint events have no events in common. So if one occurs, it affects whether the other one occurs. If one of them occurs, the other one can't. Okay? If 2 events are disjoint, they cannot both happen. So, for example, drawing a red card and drawing a black card out of a standard deck of cards are 2 disjoint events. If you have drawn a card and it's black, well, that affects whether or not that card is red. Okay? It tells you that it's not. Yes?
Are you saying like whether the card you just pulled is red or whether the next one has a chance of being red?
No, I'm saying whether that, so drawing a red card and drawing a black card are disjoint events. You can't do both in a single pull. Okay? So let's take a look at this example, an experiment to determine the effectiveness of using Prozac to treat anorexia, and this is an actual study. 53% of the subjects were given Prozac, while the rest were given a placebo. 72% of the subjects were healthy at the end of the experiment, while the rest had suffered a relapse. If 34% of the subjects were healthy and had been given the placebo, is having a relapse independent of having been given the placebo? For me, and you can reason through this, and some people really can, I find it overwhelming. It's just too many different numbers and too many different combinations of things, and I'm never sure, do I have the right combination? So what I'm going to do is make a table out of this. So I'm going to have two things: Prozac, no Prozac, placebo, no placebo. Oh, sorry. It's Prozac and placebo. And it's healthy and suffered a relapse. Those are all the different things that can happen. And then I'll put those things into the table. So 53% of the subjects were given Prozac. And the rest were given a placebo, so we immediately know that 47% were given a placebo. 72% of the subjects were healthy at the end of the experiment, which means that 28% had relapsed. If 34% of the subjects were healthy and had been given the placebo, so that's 34% here, healthy and placebo, then we can figure out what percent had Prozac and were healthy, right? Subtracting 34 from 72 gives us 38%. And then it says, is having a relapse independent of having been given a placebo? So let's figure out the relapse percentages. So this is going to be 13%. 15? 34 plus, I'm sorry. Oh, this one. Sorry, I thought you were telling me this one was 15, and I'm like, I know I've made a lot of mistakes today, but I'm okay at subtracting usually. Okay, and this one's 15%. So, is having a relapse independent of having been given a placebo? So the probability that you got a placebo given that you had a relapse all right, so that's a probability that you had a placebo and had a relapse, 13%, divided by the probability that you had a relapse, 28%. That's about half. %, 46.4%. Now, when we're talking independent, again, we want to compare it to the probability of that original thing happening. So what's the probability that you got a placebo? Yeah, it's 47%. Are they exactly equal? No. Are they close enough for statistical purposes? Yes. These are independent. Usually what you will do when you give an answer on something like this is you will hedge your bet. They're likely independent because of how close these are. You can also just, at least if you were only asked the question and weren't asked to give a reason for it, look at this. The percentage of people who had a relapse, 15% got Prozac, 13% got a placebo. That's really close, right? And this is 38 and 34. Not as close, but close enough for me to go, I would look a little further. So those are likely independent of one another, is usually what you end up saying. All right. So, the authors of your book seem to like using tree diagrams in some cases. I think that they are cotton-headed ninny-muggins, with all due respect. Pardon? There you go. Thank you for getting the reference. They do the following example with a tree diagram, and I didn't follow it until I did a table. So, the test for tuberculosis is about 99% effective, meaning that only 1 in 100 will give a false positive, and has a false negative rate of 1 in 1,000. If the incidence of TB in the U.S. is about 5 cases per 100,000, what is the probability that a person who has a positive test actually has TB? It's an interesting question. I really, honestly, I can't do it without a table. All right? So they either have TB or they don't have TB. And they got a positive test or they got a negative test. All right. So this says, when it says 99% effective, that means 99% of the people who have TB will get a positive result. 1% will have a false negative. And you're like, okay, a false negative. So that means that they have TB, but they didn't get a positive result on the test. One of the things that kind of bugs students, at least a little at first sometimes, is that in medical terms, a positive result is a bad thing most of the time. Yes, sir?
Would it be 1% or 0.01? Because 1 in 1,000 correct.
No, this is false positive, 1 in 100. So this means they had TB.
I thought a false positive
I'm sorry.
didn't have it.
I'm sorry. Hang on a second. My fault. They have a false positive, meaning they have a positive, but they don't have TB. So this is going to be 1%. Which means then a false negative is where you don't have TB, but it says that you, where you have TB, but it says that you do. So that's 1 in 1,000, so that's 0.1%. If the incidence of TB in the U.S. is about 5 cases per 100,000, So this is going to be how many people in the U.S. actually have TB. So 5 out of 100,000 I don't like that. Is this really, really tiny number? It is 0.00005, which I could have done without a calculator if I just thought about it. This is tens, hundreds, thousands, 10,000s, 100,000s. Okay, the only problem with the way that this is written now is that that's not a percent, right? And these are percents, which can get confusing. So if you have 0.1%, this is 0.001. That's 0.1%, which makes sense, 1 out of 1,000, right? And let's write this as 1 out of 100, so 0.01. This number now is incredibly low. If I take the 0.00005 and subtract this from it, okay, I've got to start using my notes on this section because I've totally stuffed something up. Oh. Stupid. Hope you're using a pencil.
It's the brain tumor.
It's the brain tumor. Do you remember that story?
I do. I feel like most of my memory is Mr. Davis stories from the probably combined 4 or 5 years you've taught us.
Okay. So of this number, so out of these, when we were doing the percent, we were doing, it should be that percent of the people who have TB. So of the people who have TB, you get a false negative out of 1 in every 1,000. So that's going to be this number times 1 out of 1,000. Does that make sense? That's an incredibly small number. And then that means that you're going to get a positive on this 0.00005. I do the right number of zeros, 4 zeros, 1, 2, 3, 4, yeah, times 0.999. So the overwhelming percentage then don't have TB. So this is going to be 0.99995. And then we get false positives out of 1 in 100. So that's going to be 0.01. That's the 1 out of 100 times 0.99995. And then this will be 0.99 times 0.99995. If you multiply these two fields together and multiply and then add them together, you get 0.01004945. That's actually a number that we need because we're looking for the probability that someone has TB given that they got a positive test. So that's TB and positive. And when you multiply these two together, you get 0.0000495. And then we're going to divide that by this probability, 0.01004945. Which is 0.0049 something, which is less than 5%. Yeah. Which means that if you get a positive TB test, you should take the test again. There's less than a 5% chance that you actually have TB, at least if you're in the US. And this is true of a lot of medical testing. With a lot of medical testing, what happens is in order to not get false positives, it's set up so that if you do get a positive, yeah, you really should have a second test or a different test frequently. Yes?
Why would you need a different test if the likelihood is so low that it's wrong?
So, yeah, in some cases what happens is you do that test and it kind of screens you initially, and then they'll do a different, more expensive test for the second one. Which makes sense. With medical testing, what you don't want is a false negative. Because what happens if you get a false negative? You think, oh, I'm perfectly healthy, and you go on your merry way. That's bad. Okay? A false positive is more to be desired than a false negative when you're testing for something that could kill the person. All right. So then the general multiplication rule, we did the general addition rule. If we take our conditional probability rule, which is the probability that B occurs given that A has occurred, is equal to the probability that B and A occurred divided by the probability that A occurs, and multiply both sides by the probability of A, we get the general multiplication rule, which is the probability that A and B occur is equal to the probability of A multiplied times the probability, oh, come on, the probability that B will occur given that A has already occurred. And this works whether A and B are independent or not. If A and B are independent, then this probability will just be the probability that B occurs. Right? That's our original rule. So let's take a look at this last example. Hopefully I'll do better than I did on the last one. Globally, about 8% of men are colorblind. And that covers all sorts of different degrees of colorblindness, by the way. Okay? There's, you can have very light amounts of colorblindness all the way down to where someone is completely monochromatic, where they can't see color at all. Okay? While only 0.5% of women are similarly identified. If 52% of the students are Rice or male, what's the probability that we choose a student at Rice at random and we get a colorblind male? So we want the probability that they're colorblind and male. That's going to be the probability that they're colorblind multiplied times the probability that they're male, given that they're colorblind. And when you do it this way, you don't have all the information that you need to do it. But remember that we can reverse that. Do it as the probability that they're male and colorblind. That will be the probability that they're male times the probability that they're colorblind given that they're male. And that we do know. The probability that they're male is 0.52. And the probability that they're colorblind given that they're male is 8%, so that's 0.08. So that comes out to be 4.16%. All right, here we want the probability that they're female and not colorblind. Well, that would be the probability that they're female, we know that, times the probability that they're not colorblind given that they're female. Well, the probability that they're female is 48%. The probability that they are not colorblind, given that they're female, is 95.5%, so that's 0.955. So this comes out to be 47.76%. Yes, sorry. 99.5, not 95.5. Thank you. And then real quickly, drawing without replacement. Remember that the probability it changes if you don't replace. That's another example of conditional probability. So if you're using a standard 52 card deck, what's the probability you would start dealing out cards and the first two cards would be hard? Well, the probability the first card is a heart is 13 out of 52, right? But what's the probability that if the first one was a heart, what's the probability that the second one is also going to be a heart? 12 out of 51, exactly right. So this ends up being 5.88%. All right. Have a good one.